Number 36. Suppose we replace the 4 kilogram book in exercise 9.31 of the biceps muscle with an elastic exercise rope that obeys Hooke's law. Assume its force constant is K is equal to 600 newtons per meter. Letter A. How much is the rope stretched past equilibrium to provide the same force F sub B as in this example? All right. So basically what they're asking for is they're saying replace the book. Pretend now there is a exercise band of sorts attached now to the hand right here. All right, and it has a an elastic component to it. It's fixed to some object, I guess, down here. And what we want to do is we want to figure out how much this elastic band has been stretched when a force equal to F sub B is applied to this exercise band. Now, we do know what F sub B is from the last problem, all right? Not from the last problem, but from exercise 9.31. So I'll write it over here. F sub B originally, actually I'll write it up here. F sub B originally was about 470, all right, newtons. So basically they're saying how much is this elastic rope stretched past equilibrium if a force of 470 newtons is applied to this rope and its force constant is 600 newtons. All right. So for letter A, it's basically, it says it right in the problem, Hooke's law. All right. So we essentially have F is equal to Kx. Right. So now in terms of, technically if there's a negative there, whatever. We know what directions we're talking about here. So the force that's applied. So basically we're trying to find the change in displacement here, right? The x value. Just dividing both sides by k, we're going to get F over k. And then the change, right, in displacement here is going to be the force, the 470 divided by the 600 newtons. And here we go. Just plug it into the calculator, pretty straightforward. And that's about 0.78, it looks like. So 0.78. I'm going to use 2 sig figs. You could go out to 3. There's no decimal here. Technically, there's 1. It's all a whole bunch of crazy stuff. Anyway, so that looks good enough to me. So that takes care of then letter A. That's how much the elastic exercise band would have been stretched past equilibrium, right? And this is in terms of meters. All right. So now for letter B, let's see what it says. It says, what force is on the biceps muscle if the exercise rope is pulled straight up so that the forearm makes an angle of 25 degrees with the horizontal? All right, it says assume the biceps muscle is still perpendicular to the forearm. So basically, here's the original picture when the arm here, the red, that's not red, that's black. When the black bar is parallel to the horizontal, okay, now we have to tilt it at an angle of 25 degrees. So I'm just going to take this picture, copy it quickly, copy, all right. We're going to paste it. And now what I'm going to do is I'm going to rotate it. All right, I'm going to try to rotate it about 25 degrees. Okay, so here's our new picture. I'll leave it over here actually. All right. Now, the force that the bicep is applying is still perpendicular, it said, to the forearm. So I'm going to leave that alone. These two force vectors, though, the force at the elbow joint is still pointing straight down, and the weight of the arm, that vector is directly down. Okay, so those are not parallel. All right, so what I'm going to do here is, let me just reorganize these a little bit. So we'll just rotate this one. All right, resize. Oops. Have to circle the whole thing. Sorry, just bear with me. All right, so we'll put that now. We'll move that now right there. That looks good. And then the same thing for this particular vector. Right, it points straight down. So we're just going to point it straight down ourselves. That looks about good. We'll move it right to about there. And there we go. Okay. So now they told us that the arm is going to make an angle of 25 degrees. By the way, I decided to draw it, 25 degrees above the horizontal. you could have done so to do it below. It doesn't matter. We're going to come up with the same answers. All right. So again, the angle in here relative to the horizontal is 25 degrees. Okay. Now what I'm going to do is I'm going to back out just that dotted line for now. You can draw it in your picture, but to me it's getting a little busy. So I'm going to leave it out for now. All right. Now what I need to do is we're looking to find F sub B. Remember, there is another force that is applied to the end of the arm. Okay, and that force is going to act straight down as well. Okay, the force of the elastic band, right? And what was the force? Well, we decided that that force was equal to 470, which was the old value in the original problem of F sub B. So I'm going to write that down. Well, that's not exactly, that looks better. So here the value now, this is, I'll call it the force, you know, of the, I don't want to say E, I'll just say F sub, well then I can't say B because I was going to say band, but I have B for the bicep. I was going to say E for elastic, but I have E there. So let's just leave it F. That's going to be 470 newtons. Okay, so now we know, I don't know if it says, does it say that it's held statically? No, but I mean, we're going to have to assume so because we don't know any rotational items, you know, as far as rotational variables. So we have to assume that this is a static problem, and therefore the sum of the torques and the forces is going to equal 0. So let's start with that idea. So the sum of the torques is going to equal 0. How many torques? Well, there's going to be 3 torques. Why? Because there are 3 forces acting at a distance to the axis of rotation here. All right, so I'll say the torque produced by the bicep. Now that should be positive because if this force is applied, it rotates the bar counterclockwise. The weight of the arm, right, that force, the torque that's produced by that force would rotate the arm clockwise, and therefore that's going to be negative. So minus then torque produced by the arm. And then similarly, the force of the torque that's produced by the force of that exercise band is going to be, also would rotate the arm clockwise. So I'm just going to leave minus T because I didn't give a subscript. It's going to equal 0. Remember what we're after here. We're after the force on the bicep muscle. So therefore, I know the force is tied into this that torque, excuse me. So therefore, I'm going to solve it for that already. So torque of the bicep is going to be equal to the torque of the arm plus the torque produced by that exercise band. Okay, now I can expand on these, right? I mean, we've seen this pattern several times now. So now I'm going to say, I'm going to do this all in terms of perpendicular lever arms, okay? Instead of doing the sign, I'm going to do it, you know, diagrammatically here. So all these R's will represent perpendicular lever arms, okay? So the perpendicular lever arm of the biceps muscle multiplied by the force that the bicep applies is equal to the perpendicular lever arm for the center of gravity of the arm multiplied by the weight of the arm, aka the force of the arm. So maybe I'll just back that out and just write WA. And then plus add to that the, perpendicular lever arm for the exercise band, and then multiplied by the force of that exercise band. Okay, so now if I want to solve for F sub B, I got to divide everything out by R sub B, right? So I'm going to just do that in one step here. So this would be R sub B. I'll just erase it over here, and here is our formula to solve. Now, do we know everything? Well, we basically do, right? We're going to have to do a little work figuring out the perpendicular lever arms, but that shouldn't be a problem. So I'm going to start writing the values all the way over here on the left-hand side now. So F sub B will equal the perpendicular lever arm for the weight. So remember, if I remember how we approach this, okay, here's the force. You dot the line of action. Okay, dot the line of action, right? And then what you would find is you would find the perpendicular distance between this line of action and the axis of rotation. And when I say perpendicular, you might say, well, perpendicular in terms of what? Perpendicular is a relative term. Perpendicular to the line of action. So that means that if I were to now dot this line on over, notice how the angle in here is a right angle. And this dotted line right here that I just drew represents the perpendicular lever arm, okay? Now we have to find this distance. So notice what the triangle looks like here. Here's the hypotenuse, here's the base, and here's the height. Okay? I know this angle in here is 25 degrees. So how do I now, knowing this weight, or I should say knowing, right, this particular knowing this particular piece, I know the hypotenuse. That's what happens when there's so many lines going everywhere. Remember, I know this distance, right? It's 16 centimeters. Okay, so I know the hypotenuse of that triangle, and I want to find this height of the triangle, and I know the angle in here is 25. So what's the relationship between the hypotenuse, this side of the triangle, and this angle? Well, it's related via cosine, right? Because this side is the adjacent side. All right, so that's why I don't like to use this particular formula sometimes. Because you might just, if you don't think about it, you might just say, oh great, I know it's 25 degrees, let me plug it in, sine of 25, get my answer. Unfortunately wrong. All right, so think it through. It's better to draw a diagram, and then even though there's a couple lines all over the place, I think it increases the probability of you getting it right instead of just saying we're following this formula blindly. All right. So that being the case, let me just back out. All right. Remember, I said it's going to be a cosine problem. So I'm just going to erase everything. You can keep it on your paper. Feel free to copy it. But I just want to make my diagram a little less crazy. So the perpendicular lever arm here, when we're trying to solve for R sub A, is going to be then equal to this distance of 16 centimeters. By the way, I'm going to convert it into meters. Okay, so 0.16 meters, multiplied then by the cosine of 25. Okay, that's the perpendicular lever arm. Multiplied then by the weight of the arm. So the weight of the arm then would be, and I already noticed I'm going to start running into my other work, so we'll move that over. The weight of the arm, you know, they told us that the mass of the arm is 25 kilograms, and therefore just take, sorry, not 25, 2.5, and then multiply that by 9.8. Okay, so this is the whole torque for the arm. All right, and I still notice I'm going to be running out of some room. Let me move it right down there. All right, then plus, now I got to do the same analysis for the exercise band, but if you notice, it's pointing in the same direction, right, as the weight is. So therefore, in terms of the angle, right, here's the line of action. Again, I know this is 25 degrees. I'm looking for this side, which is adjacent to that angle, and I do know the hypotenuse length. Okay, remember, I didn't draw it in my picture, but the length between the elbow joint and where the book was along this forearm was 38 centimeters. Okay, so what I will do is just draw that into the picture here and create a little black line underneath. All right, and just I'll move that up slightly. Okay, and that distance there is going to be 38 centimeters. Okay, so doing this again, so converting that into meters, 0.38, multiplied then by the cosine of 25. It's still a cosine, same exact format as the other problem. Multiplied then by the force applied, and we said that the force is going to be equal to 470 newtons. So 470. And then all divide that by then the perpendicular lever arm of the bicep. So notice the bicep, they told us, still stayed perpendicular to the forearm, and therefore the perpendicular distance between this line of action and the axis of rotation is just 4 centimeters. There's no cosine there. Okay, that's how the problem changes. All right. That's why we will not get a value that is or similar to the one we solved for in the other problem, because the cosines here will not cancel because there is no cosine then in the denominator. All right, whoops. So, plugging in 4 centimeters in terms of meters, 0.04, and la-di-da. Just calculate now. So F sub B will equal, hopefully I don't make a mistake on this now, calculation. So 25, 0.16 times cosine of 25 times 2.5 times 9.8 plus 0.38 times cosine of 25 times 470. That whole thing divided by 0.04. So we get a value, pretty high value of, I'm going to do 2 sig figs here. You know, sounds reasonable. It should be 2. So it should be 4,100 about. 4,100 newtons. All right. And that is the force that the bicep is applying. Guys, thank you so very much for tuning in. Please remember to subscribe. And if this video helped you at all, please hit that like button. Definitely makes a difference in terms of our end. And if we were able to help you out at all, that'd be a small way to help us out. All right. So I thank you very much. Look forward to helping you with the next question. Take care.